So we're talking about this representation of a Coxeter group by reflections, at least in the finite case. So we've been talking about how in the finite case you can really represent it in Euclidean space as a bunch of reflections in a real vector space. And last time we talked about how basically each one of the roots defines a hyperplane, and then if you take the hyperplanes out, then you get exactly the fundamental chamber, and then these other chambers, each one of which corresponds to a group element acting on the fundamental chamber. And then we talked about how the lower dimensional faces first of all, I labeled the faces of my fundamental chamber. The facets are C1 and C2, corresponding to reflections 1 and 2. And then the lower dimensional facets are just intersections of these things. So for example, this is a lower dimensional face of this cone, and I label it C1, 2. And I talked about how by doing that, I can naturally give labels to all of the faces of my hyperplane arrangement in this way. So each face can be obtained by one of the faces of the fundamental chamber once I act on it by a group element. We also talked about how the faces inherit labels where the second part is unique, but the first part may not be unique. So for example, we talked about how this can be called S2C1 or S2S1C1. But if you're a conjugate of the black phase, then you cannot be a conjugate of the green phase, for example. So this is unique, this is not. Okay? And I want to prove a couple more things about this situation. Let me first remind you that we proved a proposition last time that if I take some subset of my vector space, then the subgroup of W that fixes U is generated by the reflections fixing U. We proved this last time. And so this refers to any arbitrary subset of my vector space V. But now I want to be a little bit more concrete in the special case where this set U is one of the faces in my picture. Okay? And so here's a theorem. By the way, maybe before I say this, let me just remind you that so we define the fundamental chamber to be the set of points in the vector space such that their dot product is positive with all the positive roots. And we talked about how it's enough to check it for the simple roots. And if your dot product with alpha 1 and alpha 2 is positive, then of course your dot product with any positive combination of them is positive. Okay? And I defined C sub I where C sub I was one of the faces of C, and it's obtained by demanding that the inner product is 0 for some of the roots and positive for the other roots, the other simple roots. Okay? This is how I define C sub I to be for each subset of my simple roots. Okay. So let's go to this picture over here and make sure that this matches. So my fundamental chamber is C, where the dot product with alpha 1 and alpha 2 is positive. Now, C1, I said, was the things that are orthogonal to the vector alpha 1 and have positive dot product with respect to alpha 2, which goes like this. And so C1 is really this face, C2 is this face, and C1, 2 is the intersection. Okay? And so that's algebraically what I'm defining here vectorially. And I want to make this precise in this case. So proposition, if I have any subset of S, then the subgroup fixing I is precisely, the subgroup that fixes C sub I. The answer is basically as nice as it could be. I want a subgroup of W that I need to associate to a subset of simple roots, and so the only natural choice is the parabolic subgroup. The parabolic subgroup W sub I. And so again, let's see what that says in this picture. In this picture, again, this is a picture for S3. My Coxeter diagram looks like this: S1 and S2. And for example, if I want to know what are the things that fix C1, well, there's only two things, the identity and the reflection S1. And that's the subgroup generated by S1, the parabolic W1. This thing is fixed only by the parabolic subgroup generated by S2. And then C1, 2 is fixed by everything. And so it's the parabolic subgroup generated by both S1 and S2. So this example is too small to be anything exciting, you know. But this is true in general. Okay. So let's prove this. So I think one part is easy, which is to show that the elements of Wi really do fix Ci. So to prove that, it's enough to prove that each one of the generators fixes Ci. If the generators don't touch Ci, then no matter how I combine them, I'm still not going to touch Ci. So let's take one of the reflections, one of the simple reflections that live in here, and let's take something that lives in Ci. And I need to show that S lambda is equal to lambda. But what's S lambda? Well, by definition, S lambda is the reflection that looks like this. Right? Where this is the simple root corresponding to S, and because S is in I, this simple root is in delta I. Yeah? But if lambda is in Ci, then the dot product with things in delta I is 0. So that means that this number is 0, which means this is equal to lambda. So that part is pretty easy. The part that takes a little bit more work is to prove the opposite. That if you have a group element that fixes Ci, then it really is generated by these simple reflections. So let's suppose that W fixes some element W of my Coxeter group fixes Ci. Okay? Now, let me point something out to you. And again, maybe it's easier if we look at this picture while I point it out. Here I'm saying that I have a group element that fixes, for example, C1. Okay? But remember that it's not possible for a group element to take one point in the fundamental domain and send it to a different point in the fundamental domain. So that means that if my group element W fixes this whole face, then it has to fix it point by point. Every point has to be fixed because I can't send this point to some other point. Okay. So W times lambda is equal to lambda for all lambda in Ci. So it doesn't just fix the face, it fixes it point by point. Okay. Okay. Now I want to prove that W is in the parabolic subgroup W sub I. And so what I'm going to do is, remember we have this property that we can write any group element uniquely as something in the quotient times something in the subgroup. And then, of course, what we would like to show is that actually this is not here, and that W is just an element of the parabolic subgroup. So I need to prove that W super I is the identity. Okay. Now, let me observe something, that if I take any generator in I, then by the definition of the parabolic quotient consists of the things that when you multiply them by generators in I, you become bigger. In other words, a reduced word for W super I cannot end in a letter of I. Okay? Now remember, the nice thing about whenever we have something like this is that we can translate it to a geometric statement that says that the way that W super I acts on the corresponding root is that it makes it positive, where alpha is the corresponding root to this guy. In other words, alpha is in delta I. Okay? So this will be useful. Because it's telling me what this W super I does to my roots that I care about. Okay? Now, like I said, I need to prove that W super I is the identity, and so let me do it by contradiction. So suppose that W super I is not the identity. Okay? So then what I can say is that I can find some root, some positive root that this element sends to a negative root. Why? Because remember that if I take a group element, then the number of positive roots that it makes negative is the length of the element. Yeah? So if it's not the identity, that means that the length is positive. That means that at least one root that is positive is getting sent to a negative root. So I find some root beta such that beta is positive, but when I act on it by W super I, it becomes negative. Yeah? Now, the thing is that if I combine these two things, I'm going to get immediately that beta is not one of these roots because these roots have positive inner product with W super I. So what I get is that beta is not in delta I. Okay? So what I'm going to do now is the following. I know that W lambda is equal to lambda by assumption, right? Now, I also know that W sub I of lambda is equal to lambda. And why is that? You see, the thing is that lambda is in Ci, and I already proved that all of W sub I fixes Ci. So because this guy is in the parabolic subgroup, it fixes lambda by this first part of the proof. And so you can imagine, and kind of what I want to do is divide, but of course I can't really divide. But, well, basically I can, because I can do the following. I can say, what is W super I of lambda? I mean, what I want to say is that it's also lambda. How do I do it? Well, I can do it because I can say, okay, well, lambda is equal to W sub I lambda. Right? Because W sub I fixes lambda. And now this is W lambda, which is lambda. So that means that W super I also fixes lambda. And then I think I'm done. And the reason I'm done is the following, that I know that beta is not in delta I. So if I take the inner product of beta and lambda, what's going to happen? Well, lambda is in Ci, and I'm taking the dot product with one of the roots that is not in delta I. So if I come here and look carefully at what that is, lambda is in Ci, and I'm taking a dot product with a root that is not in delta I, so I'm in this situation, and I have a positive inner product. Okay. Now, what I want to do next is say the following. Remember that this bilinear form, and all of these bilinear forms that I've been considering, both in the Euclidean case and in the non-Euclidean case, I can act on both arguments by the same group element without changing the answer. So I know that if I act by W super I on both sides, I'm going to get the same thing. This is this thing that we've used a couple of times and that I asked you to prove. Okay? But now what happens? Well, supposedly this is positive, but I claim that it's not positive. And the reason it's not positive is that what's this? Well, W super I lambda is lambda, and W super I beta is negative. So I'm taking lambda, which is in my fundamental domain. I'm taking the dot product with a negative root, and so that's going to have to be negative. But I just proved that it's positive. So that's my contradiction. Okay. So this is a contradiction. And I conclude that my assumption was wrong, that W super I was not the identity, and therefore W is equal to Wi. W sub I, which is an element of big W sub I. Okay. Any questions about this argument? So let me now tell you, given this, what's an equivalent way of thinking about this picture? The thing is that to us right now, C1, C2, etc., these things are geometric objects. Okay? But by this proposition, I can basically think of Ci and Wi as being the same thing. Ci is the things fixed by Wi, and Wi is the group elements fixing Ci. And that provides a dictionary between geometric faces in this picture and parabolic subgroups. Okay? And so what I would like to do now is basically look at this same picture, but label it differently. By saying, for example, this is the face that is fixed by W1. This is the face that's fixed by W2. What about this one? What's this fixed by? It's fixed by nothing, right? If you take any group element, it sends this somewhere else. So these guys aren't fixed by anything. What about this guy? Well, this guy is fixed by the whole group. No matter how you reflect it, it stays put. And then it's just as natural to say, well, let me label this face by S2W empty, etc. For example, this one, I want to label it as S2W1, yeah, because it's kind of, you know, S2 is this reflection, and this is W1. Okay, and so you see what I can do then is that the same picture I can label it, but instead of putting kind of these phase names, I can label each face of this picture by either a parabolic subgroup, if it's in the main face, or a coset of a parabolic subgroup. Yeah. And this is kind of an amazing result. It basically tells you that the faces of this hyperplane arrangement are exactly in bijection with the left cosets of the parabolic subgroups. So I think that deserves to be written down. So the faces of the arrangement correspond to the left cosets of my parabolic subgroups. Okay. And this gives me kind of a nice exchange between the geometry and the algebra. So let's think about this again. I started with this algebraic object, which was a Coxeter group, and I said I wanted to represent it geometrically. Okay? And then by playing with that geometric picture, I landed at this. But you see, the reason I keep drawing this picture is because it's the only one that I can safely draw in front of you. Sometimes when I'm really careful, I can draw the next example, and that's all I can draw. Okay? And so my point is that even though this is a nice geometric picture and we can now do geometry, this picture is still hard to play with. It's hard to draw. And so if you start getting confused by the higher dimensional geometry of the situation, you can actually translate back to algebra. And you can think of this picture, or you can think of this as an abstract algebraic version of this geometric thing. But now the algebraic thing that I ended up with is richer than what I started with. I have this additional algebraic structure that the geometry suggested. Okay? And this is where I think the interplay between algebra and geometry is really useful in Coxeter groups. Now, let me make this concrete in a vocabulary that you may or may not know. Again, because this picture is too high dimensional, we like to draw it in one lower dimension. The point is that, you know, this is all a fan. It's a cone at the origin. And so if I tell you what I see here, you can tell me what the picture looks like because it's just the cone. Okay? And so instead of drawing this thing right here, I prefer to draw it as just intersecting with that unit circle in this case. Okay? And it's going to just look like this. Okay? This is W1, W2. S2W1. You have to be a little bit careful to label these things properly. This is S2, S1, W2. This is S1, S2, W1. And this is S1, W2. Okay. So these are the points that I see on my circle. And then I see these, basically these, you know, if I see a full face here, I can just represent it by telling you that I see a connection here. And if I connect these two, that implies, because this is a fan, that I see the whole thing. And so I just draw it like, and I could draw it curved, but I prefer not to draw it curved. So I'm just going to draw it like this. And now, the way I can think of this is that I can think of it combinatorially as something that is called a simplicial complex. So I'll tell you what a simplicial complex is, but this is called the Coxeter complex. Okay. So what are the vertices of this thing? The vertices are basically going to be the, you see in this case, this, I have to be a little bit careful. The vertices are the largest parabolic subgroups that are not the whole thing. Yeah. Why is that? The full dimensional thing is the smallest parabolic subgroup. The lowest dimensional things are the biggest parabolic subgroups. And so the vertices of this thing are basically the biggest parabolic subgroups and their cosets. Okay. So left cosets of the maximal proper parabolic subgroups. Okay. So to define a simplicial complex, first you have to say what the vertices are, and then you have to indicate how you're going to connect them. So for example, why did I choose to connect these two guys and not these two guys? Well, the reason that I decided to do it is because that's what I saw in this picture. Okay. But if we want this model to be an algebraic model, then I don't want to have to go to this picture and visualize it geometrically. I want to give you a combinatorial rule that tells you how do I know when to intersect things, when not to intersect things. Okay. Now, I think if I write these things out, then you'll see what the rule is. So W1 is consisting of the identity and S1. This is the identity and S2. This is S1 times this, so it's S1 and S1 is 2. This is S1 is 2 and S1 is 2 S1. This one is S2 S1 and S2 S1 S2. And this one is S2 and S2 S1. So do you see now when I connect them and when I don't connect them? Just by looking at those brown sets. Stare at this long enough, you're going to see that basically I connect them if they intersect. Like here, these guys have S1 in common. And I don't connect them if they don't intersect. So this guy and this guy have no elements in common. Okay. And, for example, this guy, the intersection is S1. The intersection of this set and this set is S1. And if you look at what the label of this face is, actually the label of this face is S1W empty, which is a left coset. For this one, the intersection is S1, S2. intersection here is S2, S1, S2, etc. S2, S1, W empty, S2, W empty, and W empty. Okay, and so you see I join things here corresponding to the other cosets, the ones that are not maximal. Does that make sense? So what is a simplicial complex? A simplicial complex on a set S is a collection of sets, which maybe I'll call C, such that the empty set is in C, and if some set is in C, so if A is in C and B is a subset of A, then B is in C. Okay. The way that I think about this is, maybe let me just change the names of things here. So this is A, B, C, D, E, F, and that I'm thinking of as my set S. And then I'm going to have some subsets. And the way that I specify my subsets in this picture is, for example, if I put an edge here, that means that my simplicial complex contains the set A and B. Okay. If I put an edge here, it's because my simplicial complex contains the set A and F. So how do I represent, for example, a bigger set like ACD? If I want to represent it in this picture, if my simplicial complex is going to contain the set ACD, then I'm just going to take ACD and fill in a triangle. And that says that ACD is part of my simplicial complex. And what is this condition saying? It's saying that if ACD is in my simplicial complex, then AC has to be in there, CD has to be in there, AD has to be in there, etc. A has to be in there, C has to be in there, D has to be in there. Okay? And so the reason these things are called simplicial complexes is because an equivalent way of seeing them is, as a bunch of either edges or triangles or tetrahedra or simplices of higher dimensions. And it's just a bunch of simplices where the only condition is if you have a simplex, then you also have every face of your simplex in the set. And so I should say that this is called an abstract simplicial complex when you present it in this way. And if you're doing topology, then you really think about these as actual simplices, and then you have to be a little bit more careful. But the point is that the Coxeter complex I can define as the vertices are the left cosets, and I have a face if and only if my set of vertices intersects. So intersecting sets of vertices that intersect. Intersect in a non-empty way. So, for example, why do you not see any triangles here? Why is it that the simplicial complex is only points and edges, no triangles? Well, the reason is that to have a triangle, you would need 3 of these cosets that have a non-empty intersection. And no matter how hard you look, you're not going to find 3 things here that have a non-empty intersection. Okay? So what this means is that this Coxeter complex is now a purely combinatorial object that exactly models this geometric picture. And so I told you that this geometric picture was a good alternative if you prefer geometry over combinatorics. Well, if you prefer combinatorics over geometry, then maybe you prefer to think about it in this way. And it really goes back and forth, so it's really nice. Yeah. One thing that actually you should do, there's no more homework in this class, but it's a nice exercise, is to draw the Coxeter complex for that example that you so carefully did, S4. This is drawable. It's one of the last drawable ones. Yeah, and it's a good exercise to see how this construction works. Okay. Any questions about this Coxeter complex? Okay. Okay, let me spend the last 15 minutes of the class today giving you a rough idea of why it is that I kept demanding that W was finite so far. Because ever since I drew this picture of my hyperplane arrangement in a real vector space with chambers, I kept insisting that I should be finite, that my Coxeter group should be finite, and that way I could make it Euclidean. And so I want to explain to you now how things can fail if you're not finite. So, and not only how do they fail, but what do you do about it? Because you want something like this anyway, if you can. So what if W is infinite? So the short answer is that we can still build a Coxeter complex. But we need to do it differently because this construction doesn't work. Differently. Okay, we're going to do like business school, so we're going to do a case study. A case study on infinite Coxeter groups. I want to show you some of the things that go wrong. And I'm going to show it to you in the simplest infinite Coxeter group that we know, which looks like this. We know this Coxeter group is generated by A and B. The only relations are A squared is equal to the identity, B squared is equal to the identity. Okay? So, what does the bilinear form look like in this case? Well, so first of all, I have two simple roots, alpha and beta. One for each generator. And the way that I define my bilinear form is by saying that remember that in my bilinear form, I always got that each root had length 1. And the inner product of alpha and beta is this minus 2 cosine of pi over infinity. Now, we don't really want to say pi over infinity is 0 or anything. We just, by convention, remember, decided that this should be negative 1. Okay. So let me show you one thing that goes wrong. Here's one strange thing about this bilinear form. What is alpha plus beta comma alpha? Well, this is bilinear. And if it's bilinear, that means that it's linear in the first argument. So I can say that this is equal to alpha alpha plus beta alpha. And alpha alpha is 1, beta alpha is negative 1. So I get 0. What about alpha plus beta comma beta? Well, you should remember that actually these things are, this is a symmetric bilinear form. Okay? And so if we do exactly the same thing, you get 0. And this should worry you because what is, you know, the picture that we usually draw is here's my vector space. I have a basis alpha and beta. And what I did just now is that I just found a vector in this vector space which is orthogonal to alpha. It's orthogonal to beta. That's a little strange. Why is this vector not 0, by the way? Why is alpha plus beta not 0? Well, the thing is that the way that I define this, alpha and beta are supposed to be a basis. And so alpha plus beta better not be 0 because they better be independent. Okay? So alpha plus beta is perpendicular to everything. That doesn't sound like very Euclidean geometry to you, I hope. In fact, what happens when you compute alpha plus beta, comma alpha plus beta? Well, if alpha plus beta is perpendicular to this and to this, then it's perpendicular to everything. So this is 0. And so what we just found is a vector which is not 0, but its length is 0. And this just cannot happen in Euclidean geometry. Okay? So the word for this is that this bilinear form is not positive definite. Positive definite means this doesn't happen. Okay? This is not positive definite. And that means I'm going to have a very hard time trying to make this fit into Euclidean space. It's just not going to work. Not Euclidean. So that's one thing. Hopeless. This bilinear form cannot be made Euclidean. But let's say we're really stubborn and we say, you know, I'm going to try anyway. Let me try to make this picture precise. So here's alpha, here's beta. And I'm going to still push through the definitions and define my fundamental chamber as the things that have the lambdas that have positive inner product with alpha and with beta. Let's say that I try to push this through and see what I can get. Well, let's see what this fundamental chamber looks like. When is lambda comma alpha bigger than 0? Well, maybe the first question is when is it equal to 0? And we know that the hyperplane where lambda comma alpha equals 0, well, we just found it. It's just the one of alpha plus beta. So we just got it in red. So these right here are the points which have inner product 0 with alpha. The ones that have positive inner product with alpha are the ones on this side. Lambda comma alpha, positive. Now, which ones are the ones that have positive inner product with beta? Well, which ones have inner product 0 with beta? Exactly the same ones. Yeah? And so the hyperplane, this comma beta equals 0 is the same hyperplane. And which things have positive inner product with beta? They're the other ones. Lambda comma beta, positive. And so what is this fundamental chamber that I defined is the empty set. So this doesn't make any sense either. And so this is just an absolute failure if you try to make it fit into Euclidean space, or if you try to just imitate directly what we're doing. Okay? How do I fix this? Well, I don't have a lot of time, but let me tell you what we can do. What we can do is that instead of doing things in V, we have to do them in a different vector space. Okay? So V is generated by alpha and beta. we're going to have to do things in a different vector space, which is called the dual vector space, which you may or may not have heard of. What is the dual vector space? The dual vector space is the space of linear forms on, or linear functions on this vector space. For example, x plus 2y maybe lives in here, or 2x plus y lives in here. All the linear functions that I apply to this vector space live in this vector space. So maybe this guy has bases a and b. This guy consists of the set of linear functions on V. It's a vector space because if you add two linear functions, you get a linear function. If you multiply by a scalar, you get a linear function. Okay? Now, I have a way in which my group acts on V. Right? I know how to define S. And we have this formula, right? So a generator Si acts on a vector in V by V minus 2 V comma alpha I. So I do have a way of taking a point here and letting W move it around. Okay. But what I want to do is do that here. And so I need a rule that tells me how to take a group element and make it act on linear functions. Okay. So I need W to act on V star. And from the theory from representation theory, there is a natural way of doing this. So if you have a linear function, then you're going to send it to some other linear function. And that linear function is going to be characterized by the property that when you apply your linear function W times F to the image of a point in V, you're going to get F of V. Okay? For F for V in V. Okay? So the way so again, I take a linear function F, I need to define how W acts on it. So I need to define a linear function W acting on F. And the way I define it is by its values. I say the value of this function on W times V should be the value that F takes on V. And you have to check that this really is an action, et cetera, et cetera. Okay? But then what you're going to do is, instead of considering hyperplanes here, which is what we did, we're going to consider hyperplanes here. Okay? So my hyperplanes are going to be, or my half spaces are going to be, I need to define a half space C sub alpha and a half space C sub beta. Okay? So how am I going to define C sub alpha? It's going to be the functions for which evaluating at alpha gives me something positive. Okay? For example, if alpha looks like this, then the functions that give you something positive on alpha are the functions positive times x plus something. So this is C sub alpha. Okay, and the same thing for C sub beta. And now these are actually hyperplanes, and I can actually define my fundamental domain to be this thing. Okay. So this is my fundamental domain. I have a rule that tells me how to take a group element and make it act here. So for example, I have a rule that tells me S1 does something to this fundamental chamber. If you look carefully at what it does something like this. it does something like this. It flips it over. So it keeps this thing fixed, and it sends this thing over here. This is a computation. This is not supposed to be obvious. I'm just going to draw a picture for you. If you see what S2 does to C, well, S2 does something. It sends it somewhere, and it's actually going to look like this. Okay? And then you keep doing it. So you make S1 act on this thing, and if you do it carefully, you see that it ends up being something like this. If you let S2 act on this guy, you're going to see that you get something like this. And it turns out that you just get it exactly like this. C, S1, C, S2, C, S1, S2, C, S2, S1, C, etc. And if you do it in every way possible, you might hope that you cover the whole space, like it happened here, but you're going to find that it doesn't. What ends up happening is that you get exactly this half space. Okay. And the angles there are getting smaller? The angles are getting smaller and smaller and smaller, and they're converging to 0. And so this thing is now my analog of V. It's not a full dimension. It's not a full vector space. It's just something, and it has a name. It's called the Tits cone. So the Tits cone D is given by basically you take the union of all the images of C. And then this is the nicest geometric picture available for this infinite group. Yeah. Now it's an infinite group, so we shouldn't get too picky. I mean, the fact that we can have a picture at all is nice. Yeah. But these Tits cones can get really complicated, and I think this is actually if you like this kind of thing, this is a very good project to understand what Tits cones look like. This is one of the maybe 2 examples that I can draw. And I actually have never seen what really complicated Tits cones look like. So a project could be to draw a very, very complicated Tits cone. It's a cone, but it's convex, and I think that's about all that's known. But it's hard to say what the shape of it is. All right.
Do you even know anything about the number of generators for that?
I mean, the combinatorial structure is the same. So So you still get chambers, and the chambers still correspond to group elements, and they still intersect in this Coxeter complex way. So I mean, what I was saying here, you can still build a Coxeter complex, and it works just fine. But now it's the geometric picture that's very messy. But the combinatorics is fine. I think you have to be a little bit careful about finite versus infinite, like finite parabolic subgroups versus infinite parabolic subgroups. But if you're careful, you can make this work. So if you ever see the word contra gradient, it's a big word, but contra gradient is exactly this. So W acts on V in this way, and this is called a contra gradient action. And it's a very big word, but it just means this. So I just want you to know in case